Good afternoon, everyone. My name is Yirga. I'm a postdoctoral researcher at Naresuan University, Thailand. I work in the research team, which is led by Professor Rabian Wankiri in the Department of Mathematics, actually. Today, I will be talking on our research work titled with Neural Network Approach for Solving Support Vector Machines with Smoothing Functions. This is the outline of my presentation. It consists of the introduction, smoothing functions and the proposed model, the convergence and the stability analysis of the method, and finally I will talk on the numerical experiments and applications of the proposed model. So to begin with the introduction part, we talk about the support vector machines. What are support vector machines? Support vector machines are supervised machine learning algorithms, basically used for classification and regression tasks. But in this talk, we will only consider the classification aspect of support vector machines. So we use binary classification, actually, binary classification. So if we are given a labeled data, which is labeled as -1 and +1 classes, two classes, the primary idea of support vector machines is like finding a separating hyperplane which divides or separates the two classes perfectly. Actually, not necessarily perfectly, but the best hyperplane. The best hyperplane which separates the two classes of the data sets. So this issue is related to optimization problem, actually. How do we relate it to optimization problem? It is like maximizing the region or the margin between the two classes of the data sets. What is the margin? The margin is like the distance between the nearest points of the two classes, which means the points which are nearest to the hyperplane from each class are called the support vectors of the classes. So the margin is the distance between the hyperplane and the support vectors. We may have more than one support vectors or only one support vectors, but at least we need to have at least one support vector from each data set. So the distance between the two data sets is the margin. So we maximize the margin, which is given by the formula 2 over the norm of W. In this case, W is the weight vector, which is normal to the support vectors. So we maximize this distance, but in other words, this means like minimizing minimization problem, like it is given by this formula, equation number 1. But in this case, we may have two types of data sets in terms of separability. One is linearly separable data sets, and the other is non-linearly separable data sets. In the case of linearly separable data sets, which means the data sets can be classified or can be separated into the two classes without any error, without making any misclassification, we can separate them. In this case, we use the hard margin formulation, which means which is given by the optimization in equation 1 here, optimization problem given by 1 here. But most of the data sets in real life are not linearly separable, and in this case we impose or we accept some misclassification errors, and in the presence of misclassifications we choose the best hyperplane which separates the two classes, the data sets into the two classes. And this is called the soft margin. Soft margin means we accept some errors, and these errors are represented by loss functions, some loss functions. For example, the first loss function we use here is the Hing loss function, which is given by the problem in 2. So this problem is called the Hing loss problem, because this is the Hing loss function, where Vi in this case is the margin violation between the two classes. Maybe we may have some points or samples which violate the separating hyperplane, which means which see it on the other side of the separating hyperplane. For example, if we see this figure, here we have two data sets, one data set, but two classes of the data set, one by blue and the other by purple. So if you see in the first figure, we have one outlier, which is represented by this blue point. This is an outlier. But in the presence of outlier, we can find a separating hyperplane, which perfectly separates without any error the two classes of the data set, like it is given in this in the second figure. But this this separating hyperplane is affected by the outlier, by the one blue point here, which means the subsequent data points will be affected by this outlier. For example, if you see in the third picture, we have a point, a sample point, which is not known. Maybe it may belong to the blue points, or it may belong to the purple points. We don't know. But when we look at it carefully, practically it is closer to the purple points, but by the separating hyperplane, it is classified as a blue point, which means while the point is closer to the data sets, the purple data sets, by the separating hyperplane, it is grouped into the blue points. So this is the effect of this outlier. So what we do is we ignore, we disregard this outlier, and we find an optimal hyperplane which separates majority of the data points. But for this outlier, we accept some error misclassifications. That's why we employ this maximum of 0 and Vi as an error, the Hing loss function. The errors are represented, in this case we represent the errors by some loss functions, but specifically this is the Hing loss function. So the Hing loss has some problems. Actually, it has sparsity problem, but it only penalizes some few points. As you can see from this figure, the first figure is the Hing loss function. It penalizes some points, the points which are misclassified or which are very close to the boundary, but the other points are not penalized. You see, if you see the figure, the points which are to the left of this Vi, the margin violation, they are not penalized, which means the loss is 0 to the left of Vi. It is only penalizing the data points which are very close to the boundary. So to resolve this problem, Huang introduced the pinball loss. Pinball loss penalizes every sample point to ensure stability of resampling. So every sample point is penalized in the Hing loss. As you can see here, this is the Hing loss, the second one. Figure P shows the Hing loss for different different values of the parameter tau. This is the slope of the loss function, the loss value. So here, even though the sparsity, the stability is assured by the pinball loss, it faces the sparsity issue because every sample point is penalized by the Hing loss. So to resolve this problem of the pinball loss, Reshma introduced the generalized pinball loss. Reshma improved the pinball loss into a generalized pinball loss. What did he introduce? He introduced some parameters, and in this case, we have some insensitive zone. Insensitive zone means a zone which does not accept errors, with no errors. In this case, we have said every point is penalized, but in the generalized pinball loss, we have some zone which does not have an error. This zone, as you can see, this horizontal line, it does not have any error. So the sparsity issue of the pinball loss is resolved by the generalized pinball loss. This is the figure of the generalized pinball loss. If we take, for example, here the epsilon to be 0 and the tau 1 to be equal to tau 2, then the generalized pinball loss will be reduced to the pinball loss. So the generalized pinball loss is a generalization of the, as its name indicates, it is a generalization of the pinball loss, the standard pinball loss. But the generalized pinball loss also faces some problems. This is a differentiability problem. It has kinks at the points minus epsilon 2 over tau 2 and at the point epsilon 1 over tau 1. At these points, at this dose, it's not differentiable. So because of this non-differentiability, we cannot apply the gradient-based methods of solving this optimization problem. So what we should do is we have to find a smoothing function. We have to resolve the non-differentiability problem. So Mark Monk and his co-authors proposed a method which is called the smooth version of the generalized pinball loss, which is given by 5, this formulation 5. This is smooth, but there are some problems with this also. It uses the traditional method of BFGS method of solving. Again, further, they have proposed some improved version of the smooth generalized pinball loss. This is called the smooth rescaled generalized pinball loss. The smooth rescaled generalized pinball loss puts like a boundary, bounds the loss function by the above. It does not extend indefinitely. So these are some of the traditional improvements of the generalized pinball loss. But this method of solving, the BFGS method of solving, or the traditional methods of solving these problems do not guarantee the global convergence of, and they are initial point dependent methods. They are computationally sensitive to initial points. Maybe they may end up at some local optimum points. They don't guarantee the global convergence. So to overcome this problem, we will propose some neurodynamical methods. So before that, we use the smoothing functions. We approximate the generalized pinball loss by some smoothing functions, like by the plus function or the maximum function. So first of all, we can express the generalized pinball loss function in this form. This is the form of the generalized pinball loss in terms of the maximum function. So we find the smooth approximations of the maximum function. We have many smooth approximation of the maximum function. Actually, the first thing we did is like we introduced it in our previous work. We introduced the epigraph reformulation, or we transformed the generalized pinball loss. We approximated it using the epigraph formulation. But in that case, what we obtained is like we have many parameters, and the problem became constraint problem. So in the constraints, we faced many parameters, and it was somewhat difficult to handle using the epigraph reformulation. It's a good technique actually, but it is somewhat tough to handle the parameters, and it takes too much time. So in this case, we what we propose is we use, among the different methods of smoothing techniques for the generalized pinball loss, we use the hyperbolic tangent smoothing approximation, the hyperbolic tangent smoothing approximation of the plus function. So when this one is for the epigraph reformulation, as you can see, this is the problem. This is the problem of the SVM problem, which is approximated by the epigraph reformulation. As you can see here, we have many parameters. So we want to avoid this difficulty, and we introduce this approximation, a smooth approximation of the plus function. You see here, the plus function is approximated by the tangent hyperbolic. Here the parameter mu is a smoothing technique. So with this approximation of the plus function, we redefine, or we approximate our generalized pinball loss in terms of this tan H smoothing, like it is defined in 14. So this is our approximation. So using this approximation of the generalized pinball loss, we have our optimization problem. But before going to the optimization problem, we have to make sure that as we are removing the non-differentiability property of the generalized pinball loss, we have to make sure that this approximation is differentiable, and it also really approximates the generalized pinball loss. So we have these two properties. We have proved these two properties. One is the differentiability of the approximation, and the second one is like if it really approximates, what happens? How is it the approximation, the candidate approximation approximating or approaching the actual generalized pinball loss function? So we have proved these two concepts, and this is the visualization of the smoothing and the original generalized pinball loss function. You see figure 3. If you see the values of these dotted ones are actually, here we have the solid, black solid is the exact generalized pinball loss. As it can be seen here as the kinks, it is not differentiable. So for different values of the smoothing parameter mu, we have different values of, or we have different graphs of the approximation. But in this case, as you can see, what happens to, as mu becomes smaller, the approximation or the approximated generalized pinball loss goes far away from the standard generalized pinball loss. But if we let this mu, the smoothing parameter mu, to be greater or bigger, it converges to the standard generalized pinball loss. So this image supports this relation given by 15 in this theorem. As mu goes to infinity, the approximation, the candidate approximation really approaches to the standard generalized pinball loss function. So this picture is like supporting the theorem. So with this approximation, we have our generalized pinball laws optimization problem changed by the smooth generalized pinball laws. Here, this G of mu vi is the smooth generalized pinball law. So our problem is now this objective function G is a smooth function. It is differential. Now we can apply the gradient based solvers. So based on the gradient based solvers, we propose continuous time dynamical systems. Like actually we are solving this problem against the weight vector W and the bias B in the equation of the separating hyperplane. So we propose this gradient based neurodynamics 17 and 18, and we concatenate these two models into one by just concatenating or stacking. Then finally we get this model, the model 20 to 21. Like we are calling this omega to represent the concatenation of W and the bias B, like this way. So finally we stack or we compact the problem to be like dW by d omega by dt is equal to kappa times phi of W, where phi is a function given by 19. So the rest of our working will be solving problem 20 to 21. Okay. Now we transform the optimization problem into dynamical system. So if we are solving the optimization problem into the in terms of the dynamical system, we have to have some relation between the two problems. Otherwise, we start with optimization problem, then we transform it into dynamical systems. If there is no relation between the two problems, it will not be convenient, or it will be nonsense. So what we should do is, one, we have to prove the existence. This is under the convergence and stability analysis. Under the convergence and stability analysis, we have the global solution, existence, and existence of solution. So we have proved this lemma 4.1. There exists a solution of the problem, this dynamical system. There exists a unique solution. To show the existence, it is like sufficient to show global Lipschitz property of this function given by 19. So the dynamical system is proven to be the solution is guaranteed to exist, global solution. The second one is like relating the optimal solutions of the original optimization problem and the equilibrium points of the dynamical system. So here what we did is a point omega star is an equilibrium point of the dynamical system 20 to 21 if and only if it is the unique global solution of the smooth optimization problem, the SVM problem. So this is the key point which relates the two solution concepts. The equilibrium point of the dynamical system is going to be the optimal solution of the SVM problem. Okay, we have also proved this one. And finally, we have proved the global asymptotic stability. Actually, under this global asymptotic stability, there is a Lyapunov stability. We defined an appropriate Lyapunov function, and we proved that the system is Lyapunov stable, asymptotic stable, and it is globally convergent for this, we employed the Lazali invariance principle, which is stated in Kahali. So after this, we proceed to the numerical experiments and applications. So what we did was we employed the model in synthetic and UCI datasets. Actually, here I brought the only the UCI datasets. We have 6 UCI datasets here, along with their number of samples, number of features, and classes. We are classifying them into 2 classes actually. So for this, we employed the performance metrics like accuracy, MCC, the Matthew classification, and the F1 score matrix, 3 matrix actually. So some of the visualizations are here. The first in figure 4, it shows like the weight vector for the heart failure dataset. Actually, we made it to visualize the first 5 features. So that's why it has 1, 2, 3, 4, 5 features. But in practice, how many features do we have for the heart failure? We have 12 features. But for the sake of the visualization too, for the attractiveness of the visualization, we set it to give the first 5 features in the visualization. This is the bias visualization. So if you see the graphs or the trajectories, they are becoming stable. At some point, they become stable. They converge to the equilibrium point. Similarly, this visualization is for the ionosphere. It shows 5 features here, and this one, figure 7, is for the bias trajectory for the ionosphere. So, but we have to quantify them in numerics. So, for the comparison with the existing models, what we did is, this one is for the comparison of the model with 3 benchmark models. We abbreviated their names like SRGP. This stands for the smooth rescaled generalized pinball loss that we discussed previously, and this one is smooth generalized pinball loss SVM and the smooth pinball loss. These ones are the pinball family, but in different improvements. This one is the smooth rescaled, and the second one is only the smooth, and the third one is the standard pinball loss. So when you see, actually we did like I told you previously, the experiments was performed against 3 performance metrics: accuracy, MCC, and the F1 score. But for the sake of visualizations, I brought here the accuracy, only the accuracy. The results for the MCC and the F1 score are also similar to this one. So if we see the values of the accuracy for 6 datasets, we have 6 datasets in this row, and 4 models, including our model in the column. So our model outperforms in 5 of the 6 datasets. It's only on the heart failure dataset that lost. This is for the linear kernel, actually. Linear kernel without noise. Because we performed the experiment with different types of kernel, linear kernel and RBF kernel, in the presence of noise and in the absence of noise. So this one shows the linear kernel without noise. The second table, table 3, is the same data sets, the same model comparisons, but in this case it is with some noise, Gaussian noise here. So in the Gaussian, in the presence of noise, our model outperforms in 4 of the 6 data sets. It's still okay. And for the RBF kernels, in the presence of kernel, RBF kernel, but without noise, here we see the results in table 4. We won in 3 out of the 6 data sets. Relatively, in the linear kernel has better performance than the RBF kernel. But when you see in the RBF kernel with some noise, our model wins in 4 out of 6 data sets, which is better than the noise-free experiment. So I think we can conclude from this that the model is noise tolerant. It is not sensitive to noise. That's what we can see from here. As you have seen here, these data sets are relatively small data sets. The number of samples in each data set is like not more than 800, like not more than 800. So we also employed the experiment on big data sets, like for the spam page with 4,600 samples, the magic data set with 19,000 samples, and HTRU2 data set with 17,000 samples, and so on. So in this case, as you can see, our model wins in almost in 3 of the 4 data sets. You see, in the spam base, our model, the red ones are for our model, the red ones are for our model, and the blue ones are the points where our model lost. So it's only on one data set that our model lost in this experiment. So generally our model performs better than the existing models, and to show that this model is better, or to the statistical difference or the significance of the difference, we performed a statistical analysis using the Friedman test statistical analysis. This is the formula for the Friedman test statistical analysis, followed by the Nemeni post hoc analysis. So what we obtained is, in the statistical analysis, actually it's very detailed, but in general what we obtained in this case is in the linear kernel scenario for the simple data sets, the neuro SVM means the neurodynamical SVM, our model significantly outperforms one of the models, the small rescaled generalized pinball loss model, across all the 3 metrics. We did the statistical analysis in the 3 metrics, in the accuracy, in the MCC, and F1 score. So there is statistically significant difference between the neurodynamical model and the smooth rescaled generalized pinball SVM model. With the other, the remaining 2 models, there is no statistically significant difference. Actually, there is a difference. Our model wins the other models too, but statistically it is not significant. But when we examine the statistical significance of the model against the other models in the presence of nonlinear kernel, which means the RBF kernel, there is no statistically significant difference. The model still outperforms the other methods like we have seen here. For example, if you see here, this is the RBF kernel. This is the RBF kernel. It wins in 4 data sets out of the 6 data sets. But when we calculate the average ranges and compare significance, no significantly no significant difference was observed. So this is all about my presentation. Thank you so much. For any questions, you are welcome. Thank you so much.